That's right. Today we're talking about an AI that can not only play Minecraft, but can do so in large part by training on gameplay from YouTube videos. That's actually what you're looking at right now. And I don't just mean run around, maybe chop some trees down and stuff. I mean actually play Minecraft. Make shelter, mine, smelt iron tools, loot village chests, and even find and use diamonds. Within the AI and ML research community, a good deal of work has been done on Minecraft in the past several years, but reaching this level of play has yet to happen as far as I'm aware. That alone is awesome, but what I think is actually one of the coolest things in this paper is some preliminary results that show that it could be possible, on top of all this, to control these agents with natural language. So telling an agent that you wanted to go collect seeds or explore for water. It's super awesome. That's hidden all the way in the end of the appendix though, so do stick around to the end if you want to hear more about all of that. The paper about this method comes from a team at OpenAI and UBC, and it is called Video Pre-Training, or VPT for short, Learning to Act by Watching Unlabeled Online Videos. Going straight into this abstract, we can see the approach they take in this paper here, where they say we extend the internet scale pre-training paradigm to sequential decision domains through semi-supervised imitation learning, wherein agents learn to act by watching online unlabeled videos. This means that they are using massive amounts of videos of people playing Minecraft and then bootstrapping from that knowledge to have agents learn to play the game. They then take that initial model and fine-tune it with a mix of human data and reinforcement learning to further refine the agent's abilities. We'll talk more about what all that means as we get into the video, but going into this, I think this type of idea is pretty intriguing because combinations of those two types of learning, imitation learning and reinforcement learning, can give some pretty great results, as we'll see here. Another thing to note is that this study is done with native human inputs, so that means a mouse and keyboard every 50 milliseconds, which I think is another nice step towards more general agents. The last thing I'll mention before we dive in is that if you find this type of content interesting, consider subscribing. On my channel, I cover a mix of interesting big papers to keep you up to date, but also smaller topics to introduce you to new interesting ideas. I also just started posting on Twitter if you're interested in following me there. But now let's get back into the paper. As I briefly mentioned, the core of this paper really rests on the idea that you have massive amounts of video data on the internet through sites like YouTube. But the issue is that the actions taken in these videos are unlabeled, or it's not clear what buttons are being pressed. And that's an issue because that means we can't do something like behavioral cloning, or BC for short, which would generally try to map an observation from a game and try to learn the action a human would take. But again, the issue is that we don't know what those actions are, so how do we deal with that? One option to deal with unlabeled data is a group of methods called semi-supervised imitation learning. And these methods focus on, well, exactly this issue, learning from just observations with no, or at least a very small amount of action data. That is, however, not what they go with in this paper for two main reasons. The first reason they give is that these methods are susceptible to what's called exploration bottlenecks, which essentially means that it can be easy for agents to get stuck because sometimes to progress in a game, very specific sequences of actions might be required. And it's not always easy to figure out what that specific set of actions might be. A lesser example of this might be breaking blocks in Minecraft. Until you know how to break blocks, you are very limited in what you can do. And while breaking blocks may seem simple to a human, it's actually quite difficult for an agent randomly exploring. An agent has to look at a block it wants to break, and then for around 20 to 60 consecutive actions, because there's 20 actions in a second, hold down the mouse button without letting go or looking away from that same block. And the chances of that happening are very slim. The other reason they give as to why they don't use semi-supervised imitation learning is because these methods are sometimes complex, and having larger data typically mean that simpler methods start working better. So to get around this issue of data being unlabeled, they do this. We'll go over each part of this diagram, but for now, let's focus on this pink part down here. What they do is they decide to collect a little bit more data, but this time they get labeled data by hiring contractors to collect the data by actually playing Minecraft and recording all of their key presses. Now, they say they collect a little bit of data, so I guess funny enough, 2,000 hours of gameplay is just a little bit of data for them, but I guess when you compare it to the about 70,000 hours of unlabeled data that they've collected from the internet, it actually is a relatively small amount. Once they've collected this labeled data, they learn what's called an inverse dynamics model, or IDM for short. And the way this IDM works is you take two frames from a game and then use supervised learning to predict which action was taken in between the two frames. So for example, here, if you've played games before and I show you these two frames, you can probably guess that the key I pressed was the W key. And that's what this IDM is learning. The next step in this whole diagram program is labeling the unlabeled videos with this new model. So from up here, you can see that they've collected around 70,000 hours of filtered but unlabeled Minecraft videos from online. And after the step with IDM, that becomes 70,000 hours of videos with action labels attached. And now that all that's labeled, the final step can be performed, which is simply behavior cloning. This is simply what I described before, where the model sees an observation from the game and predicts what action the human took. Putting all this together, the output of this first stage of experiments is essentially a model that is trained to be quote unquote human-like, or take actions that a human is most likely to take in the scenarios it's given. And they call this initial model the VPT foundation model. So that's the setup, but how well does it actually learn and how capable is it? That is what this first set of experiments takes a look at. Here we can see the performance of the IDM over the course of the training. On the x-axis, we have the amount of hours that the model was trained. And then on the y-axis, there are actually two scales, one for the key press accuracy, so the percent of the time that the model learned the correct key presses. And then on the right, there's the R squared of the mouse movements, which is a measure of how well the model can explain the mouse movement, which has a maximum value of 1. As you can see, it takes around 100 hours of data for the mouse movement predictions to start becoming pretty reliable, or almost to 90%, and about 1,000 hours of data for the key presses to start getting to around that same level. Then overall, at 2,000 hours of training data used, the final results of the model are 90.6% accuracy for the key presses and 0.97 R squared for the mouse movements. The key presses aren't perfect, and it's likely impossible to detect all of them perfectly in the first place, but as we'll see, this is more than good enough for what they're doing here. So that was mainly about how the IDM performed, but let's also now take more of a look at the behavior cloning model, or from now on, I'll just refer to this as the foundation model. Overall, the foundation model is 500 million parameters, and it was trained for about 9 days on 720 GPUs, which is about 18 years of GPU compute power if you add it all together. We can see in this left figure that it's trained for about a total of 30 epochs, and the whole time we see improved performance, which is the main important thing here. Next to that, we can see over the course of training how commonly the foundation model agent obtains certain items. With no training, it was making essentially no progress. Though after just the first few epochs, it did start picking up some steam. For some reason though, it does seem that after about 5 epochs or so, the performance improvements started to level off. Each episode here was 60 minutes long, which means that each point here is how many of that block the agent collected in, on average, an hour. So even though it's getting some blocks, which is certainly an improvement over getting, well, no blocks, its performance is still pretty lackluster at this point. In 1 hour, the agent was getting on average less than 10 random blocks like dirt and gravel, and about 1 wooden plank. And then around every 100 hours, it was able to get a little bit lucky and build a crafting table. For anyone who doesn't play Minecraft, making a crafting table usually takes more like 50 seconds on average from the start of a new game, so 100 hours is a bit rough to put it lightly. There is still a bit more to add to this though. Apparently the agent was also able to kill zombies, forage for food, and collect items from village chests. Though given that these things were not presented in the previous figure, I'm gonna guess that the agent probably wasn't too great at those things either. But this isn't the end of the paper. The paper still has several more tricks up its sleeve. Now that they have the foundation model, the next step for them is to fine tune it. This means that instead of training on a very general set of data from all of Minecraft, they'll start from the base foundation model and train it on some extra, more focused data for the task that they wanted to perform. For this fine tuning, they gather 2 data sets. The first is called Contractor House, and again, it's just a labeled data set collected from contractors that consists of 420 hours of data of them trying to make basic houses. The second data set is called Early Game Keyword, and it's a collection of the first 5 minutes of a number of YouTube videos that meet certain keywords like New World or Let's Play Episode 1. So the idea here is that both of these data sets should be more focused on the early game of Minecraft. Then after fine-tuning separately for each of these 2 data sets, we can see the results here in figure 5. And the results here are looking pretty good. You can see some pretty massive improvements for very important blocks like wooden planks and crafting tables. And the agent is even able to, on occasion, make wooden and sometimes even stone tools, which was not even previously possible. From video samples, it's clear that this agent still isn't quite up to the level as most humans, but it is unquestionably a lot better after this first fine-tuning step. Can we still do even better though? And luckily the answer is yes through reinforcement learning. This is the idea that instead of training agents to imitate human data, we train them to maximize a reward we give them. And what you're looking at right now is the sequence of events that will be rewarded. So first getting logs will give a reward, then planks, then a crafting table, and that continues all the way up to a diamond pickaxe, which you can see is by no means an easy feat. Taking contractors requires on average over 20 minutes to complete and oftentimes even longer. The question is, if given these reward signals, can an RL agent learn to do the same thing? And if we take a look at this new set of figures, we can see that the answer is mostly yes. First off, in graph A, we can see a comparison of RL agents trained, but from different starting points, from random, from the VPT foundation model, from the early game model, and from this no KL loss thing that we'll be talking about a little bit later. And what this tells us is essentially that more pre-training significantly helped the agent. We can see that the randomly initialized agent wasn't able to achieve anything, but the agent initialized from the foundation model was able to do quite a bit, including mining coal, iron, and was also even able to craft some torches and eventually some furnaces. The RL agent trained from the early game model was able to go even further, going as far as smelting iron, creating iron pickaxes, and then remarkably even using that to find and mine diamonds and then craft diamond tools. And what's even more impressive is that aside from being able to create that diamond pickaxe, it was able to achieve all these tasks with a consistency comparable or even above that of the human contractors. This is all super awesome, though do note that the amount of compute used here was not small by any means. Each of these graphs shows 1.4 million 10-minute episodes, which totals out to about 25 years worth of experience for each one of these experiments. I by no means think that these agents should be reaching human level performance in the time it takes humans because, well, humans have a lot more general pre-training and can communicate goals through language. That being said, there's very clearly a huge gap here that I'm sure will be vastly improved in papers to come. And there is also one more issue here, and that's this agent's propensity to, well, forget the best agent was trained with an extra KL loss term that essentially stipulates that it can't become too different from the base early game model. And as you could see back up here, what happens when this KL loss term isn't included is that the model actually forgets the things that it originally knew at the start of its training, and because of that, it gets stuck and is not able to get to any of the later tasks. This issue is actually termed catastrophic forgetting in the literature, and it's actually a huge problem in reinforcement learning on most problems that are either large or cases where the agent needs to continually learn. This KL loss is one way to help solve this, but there are also many other interesting methods that focus on getting around this problem. Those are some of the final results on this paper, but how do they actually look? Well, luckily, they've actually provided some videos that we can take a peek at. As we're watching this, let me just give you a little bit of a disclaimer because I don't know, these could be cherry picked, and I'm also cutting out some parts of the videos myself so that they don't take too long to watch, though I have linked the full versions in the description below if you're interested. This specific video we're watching is actually one of its best runs, I think, because this is one of the episodes where it actually gets a diamond pickaxe. As I cut through, you can see the agent first getting wood, making initial tools, then as we go, it upgrades its tools to stone. It eventually finds iron in a cave, mines that, smelts it, and I actually thought this was really cool because it doesn't have coal, so instead it smelts the iron using a wooden pickaxe as fuel, which I've been playing Minecraft for 10 years and I didn't even know you could do that. So I guess this agent's a better recycler than I am. After that, the agent keeps mining and around only the 4-minute mark it finds diamonds, which is very lucky given that diamonds are somewhat rare, but nevertheless impressive. After it mines the diamonds, it immediately makes a crafting table and crafts a diamond pick and helmet. It is interesting how it crafts the helmet given that it doesn't receive any reward from that. I wonder if this has to do with the fact that the pickaxe would have been in that same spot had the agent only had 4 diamonds. It's very impressive, but do remember this is quite cherry picked and cut, and not all of the episodes go nearly this well. Again, there are some more videos in the description if you want to check those out. Overall, I think these results are pretty impressive, though one question that remains is whether or not this was the most efficient way to go about this. And in the paper, they do focus on one specific choice that they made and try and do some experiments to show whether or not it was a good choice. The specific idea that they focused in on was this idea to collect labeled data from contractors, then use that data to create an IDM that can then label the other 70,000 hours of data from the internet. Remember, pretty much the whole point of this paper in the first place, or at least one of their major claims, was that they could leverage the massive amount of, keyword here, unlabeled data on the internet to help an agent learn. But if they're going to have to collect labeled data from human contractors anyway, does that invalidate their results? Well, that's something we could actually test in an experiment, and it would depend on whether or not that extra unlabeled data really helped the model at all. And that's what we're taking a look at right here. They show that by training an IDM, labeling the unlabeled data, and then training on that unlabeled data, they do much better than had they just trained a behavior cloning model on the 2,000 hours of originally labeled data alone. To the left of this line is the results of training the foundation model on only contractor data. And then to the right of this line is where they start training on the open internet data. And as you can see, there are some very clear improvements. And in this next plot, we can see this is the same case even for the fine-tuned models. Fine-tuning models after training on open internet data works a lot better than when you only pre-train on the contractor contractor data. What I think we should be taking from these experiments is that although yes, it does suck to have to collect 2,000 hours of human data to be able to utilize unlabeled data, it is worth it. But wait, do we really need 2,000 hours of human data? Well, if we take a look here, it actually turns out that we don't. Remember, the main purpose of the 2,000 hours of human data was to train an IDM to a high level of accuracy so that we could then label other data. What we see here, though, is that if we take an IDM that's only been trained on 100 hours of data as opposed to the full 2,000, the behavior cloning is still able to perform really well, which means that the IDM really doesn't need to be all that accurate to benefit the later training, and that 100 hours of labeled data would have likely been sufficient. Now that we're getting close to the conclusion of the paper, you might think that that's all, right? And no, there's actually a bit more hidden away in the appendix. And I actually think that this is one of the most interesting parts of the whole paper. These results are all the way down here because they are still fairly weak preliminary results, but gosh, are they interesting. And what they show is that if you take the audio that comes with many of these online Minecraft videos, which will often be people talking about what they're doing. So for example, someone might say, let's chop some logs or something of that sort, or something like let's build a house right before they actually build a house. Well, if you actually take that audio, then convert it to text with automatic speech recognition, and then condition the agent on that text, you can actually slightly steer the model in a desired direction. For example, if you tell the model to explore, it will actually travel a little bit further than had you told it to do something else. And if you tell the model to collect wood, it will collect more oak logs than it normally would have. I love this because it is done entirely using data collected from the internet without any extra labeling needed. The results here are still very weak. You might notice, for example, that the actual difference between the amount of wood collected is less than a block in most cases. But I do hope we see more of this direction in the future. So going back over everything, how can we summarize this and also the contributions of this paper? First, I want to talk about that, and then I'll also go over some of my personal thoughts and some of my criticisms. The paper showed that by using labeled data and training an IDM, they were able to make use of massive amounts of open data on the internet. From there, they trained an agent in 3 separate steps. Step 1 was behavioral cloning on a massive set of data to learn a human behavior prior. Step 2 was to then fine-tune on a more specific set of data. And finally, in step 3, they used reinforcement learning to fine-tune the agent to find diamonds and create diamond pickaxes. Overall, the project used $160,000 to gather contractor data, but the experiment showed that the same results could likely be achieved with a $2,000 budget. Though note that that was just the cost for collecting data, and there was also likely an enormous cost associated with training agents for billions of steps. To put that into perspective, that is multiple decades of GPU compute years. Though they do open source all the collected contractor data and their models, which I think is really awesome. I wish they did this more often. Overall, I quite enjoyed this paper, and I thought it was an interesting work with some good experiments. Personally speaking, I really like the direction of learning foundational behavior models because they are a great way to bootstrap the learning of agents in many very hard exploration problems, which I think is the majority of real life problems. I mean, they are kind of already big if you're looking at NLP, and I hope more people start working on general foundation models in future works that others can then bootstrap off of. And while all in all, I quite like this paper, I do still have some minor criticisms and also just extra general comments I'd like to add. One thing that I didn't love about the paper was the author's insistence that what they achieved would be impossible with reinforcement learning alone. If we go back and take a look at what happened when they tried to learn from scratch with reinforcement learning, we can see that the agent clearly made no progress. And if we look back earlier in the paper, they explain exactly why this is. To get any reward, the agent needs to at least start by chopping 1 block of wood. And the only way for that to happen is if, while standing still looking at the same block, the agent holds down the left mouse button for 60 consecutive steps. And the chance of that last part alone happening with a random agent is 1/2 to the 60, which is about equal to 8.7 times 10 to the -19. And that genuinely would be considered impossible. What they leave out, though, is the fact that there are exploration methods in reinforcement learning that can perform much better than random search. I won't claim that any of these exploration methods would certainly be able to achieve this. I really don't know. But it certainly doesn't seem fair to me to claim that it's impossible for reinforcement learning to solve this type of task when the only baseline they're looking at is, well, the worst possible one available. The next thing I'll mention is that while this method obviously works, it's not necessarily clear that this is the best way to go about this that's been presented in the literature. Though this paper is indeed the first to create an agent that can create diamond tools, we have to keep in mind that, as far as I'm aware, this is also the first paper to work on Minecraft with these goals that use this level of data and compute. It very well could be possible that there are other works in the literature that could perform better than this if trained with the same amount of data and compute. One pro of this approach, though, is at least that it is, I think, a bit simpler than most other methods out there. And the last thing I'll mention is not so much of a criticism so much as it is a personal preference, and that is that I really hope we see more of a focus on non-supervised methods in the future. A crux of this paper was that they collected lots of labeled contractor data in order to get the whole system working. And while that is better than nothing, means that this method can't be generally applied to other problems unless you can collect lots of labeled data for that specific problem. As they mentioned in the beginning of the paper, using semi-supervised imitation learning methods was an alternative that wouldn't have required collecting any labeled data. And if they got that working instead, that would have made this method much more general and potentially less expensive to use. I can see why they avoided that direction. It's simply much more difficult. Not to mention, hiring humans could maybe be cheaper than the compute that would have been required. But at least in the long run, as hardware improves, I think that semi-supervised and unsupervised methods will be the better approaches. To wrap it up, kudos to the team. I think the paper is very interesting and a fun read. To all of you watching, if you've enjoyed the video enough to watch it to this point, do consider subscribing, maybe dropping a follow on Twitter. But anyway, thank you so much for watching, and I hope to catch you next time.